Whoa, that's loud. All right, so let's talk about bases. I don't know what the hell the plural of basis is. So first things first, um, I need a concept of a span. So I think I've already talked about this, but I just want to very carefully write it down. So the span of a set of vectors v1 through vn. So I've got some vectors, right? I'm talking about the span of this set of vectors here. Those good commas associated to them. All right, so the span of this set of vectors is, have I given this definition in here before? I've probably said this in passing at least.
Uh, yeah, you kind of told us it was like the linear combinations.
Okay, good. So this is the set of all linear combinations. So I'm going to say a vector x is in the span of this set of vectors v1 through vn if and only if, right? So both implications. If x is some linear combination, so a1 v1 plus, oops, scalars. Sorry, vector hats on v's. A's are scalars. Okay, everybody good with that? Okay, now there's some um, there's some thought here about what a spanning set is and what its kind of uh, implications are that don't seem real obvious. So my goal here is to define the idea of a basis. So first I've got a spanning set, right? So this is just a set of vectors that cover something, right? So if let's see, if I say a set of vectors, again, v1 through vn, is a spanning set sorry, I wrote for and I should have written of a subspace S if S is a subset of the span of my set of vectors. Does that thought process make sense? So basically, if I've got a subspace that I'm considering, a spanning set is any set of vectors that covers that thing. It's big enough. I need to stop my friggin' email, don't I? Where's that thing? No, fuck it. We'll just close Chrome tabs altogether. Oh my god. Stop. Phone. No. Quiet. Thank you. Okay. All right. Next thing. So I've got my idea of a spanning set. Now, a couple examples here. Spanning sets can be kind of too big or too small. Well, okay, spanning sets can be too big, maybe. So let me provide an example. So 1, 1 is a vector in R2. 0, 1 is a vector in R2. And 1, 0 is also a vector in R2. So note this thing, right? These three vectors span all of R2. Does that make sense? So this is going to be my kind of usual. I'm going to say this. this means that these three vectors make a spanning set for R2. Now you might notice that these are this feels a little big. Never going to be able to escape all the notification messages. I'm sorry. I can't teach this on a computer that's connected to the internet. It's too much. All right. So does it make sense that spanning set is too big? Okay. Why is it too big?
Because one of them is dependent on the other two.
Good. Yeah. There's some concept of linear dependence, right? This thing has a vector that is constructed out of a linear combination of the others. And so I could achieve this same span with a smaller spanning set. Does that also make sense? So in other words, we could kind of think to ourselves like, hey, let's just discard that. Which one do you want to discard? This is a weird question, actually. Does it matter? If I think about throwing one of these vectors out, if I think about geometrically, right? I've got this vector that points to the right, I've got this vector that points straight up, and I've got this other vector that points over here. If I toss any one of those, am I still going to be able to cover all of R2? You guys see that? Thoughts? Seeing this, maybe? Yeah? Okay. So, I'm going to pitch one of these. I'm going to make an unorthodox choice, and I'm going to pitch the vector 0, 1, just because I've never really liked the idea of the y direction. It's just, I've always had something against it. I don't know why. That wasn't an intentional pun. I wish I could take it back. Sorry. So this set also spans R2, right? You guys with me on that? And is linearly independent. Oh, whoops. I said dependent. What is this set?
Dependent.
Independent. Good. Okay, so I have now a linear independent spanning set. Now, this is rad because now I can make my definition that I wanted to make. A basis for I'm going to write sub here, space, S, is a set of linearly independent vectors that are also a spanning set. Does that make sense? Okay, now, crazy thing, cool thing, really actually super cool thing. Little theorem. If Vi through Vn is a basis for S, then for x in S. There are unique, and this is crazy that these are unique, scalars A1 through AN with X is A1 V1 plus on and on to AN VN. Okay, now what the hell? This is kind of cool because this means that there are coordinates. Remember how I think about R2 as like a vector that's got an x coordinate and it's got a y coordinate? Right? So I'm thinking like, okay, so hey, look. The vector, say 2, 3 in R2, I'm really thinking about that as 2, 3 is 2 times the x vector plus 3 times the y vector, right? You guys all on board with this? This is a thing called the standard basis, these x and y vectors. This is what we call the standard basis. That's super important that we know that it's only the standard. It's not the only basis, it's just the standard basis. So let's look at my earlier breakdown up here of my 1, 1, and 1, 0. I think that I should be able to decompose 2, 3 into that new basis. So I'm going to think about 2, 3 in R2 with my new basis. So I'm going to take 2, 3, and I'm going to say, all right, 2, 3 is some number of 1, 1s plus some number of 1, 0s. So can you guys help me out and figure out what these two numbers are going to be?
3 and -1.
Nice. Are you sure there's no other options?
Yeah.
I'm gonna bring this around in a really cool way. So this is a neat thing about linear algebra is that you can always kind of wrap it back to something you know. Here's the thing I'm going to wrap this back to. I'm going to look at this 2, 3, right? And I'm going to think, what does this thing remind you of? What is that sucker?
Column picture.
That's exactly the friggin' column picture, right? So I've got my two vectors in here, and I multiplied by this vector 3, -1. How do I know that this is the unique answer? What's special about that matrix right there? What is special about this matrix right here? What is the thing I know about a matrix with linearly independent columns?
It's invertible?
Hell yeah. It's non-singular, it's square, it's invertible. What does it mean that it's invertible? Dude, that means that that's the only answer. You guys see how that wraps all the way back? So this is kind of a really cool thing that a basis, right, has this property that if you throw it in a matrix, the columns are linearly independent. Duh. And that means that it's going to have unique decompositions. It's really rad. You guys good with this? Okay. So, aside from my excitement about this, are there any other questions throughout this kind of thought process? There's one more thing I want to define before I go on, but I want to make sure we're not confused on anything. You guys good on all of this so far? Okay. Last thing. The dimension of a subspace, and I guess I wrote sub here. Doesn't have to be a subspace, could be a whole space. So the dimension of a subspace is the number of vectors in a basis for that subspace or space. Does that kind of bring this full circle? So remember, R2 is probably two-dimensional, right? How many vectors do I have to span it? Well, I have to have at least two. How many can I have that span it that are linearly independent? At most two. Ergo, the dimension of R2 is 2. That shouldn't be a huge surprise, but now I can use this on subspaces, right? So I can say, okay, so if I construct a funny little space, right? So just for example, and I promise we'll do a homework question here. So for example, what is the dimension of S, the span of the set of vectors 1, 0, 0, 0, 1, 0, and 1, 1, 0. That was the worst bracket ever. I'll fix my brackets. What do you guys think? Yes, still bad. All right, what's the dimension of this space? It's got 3 vectors in it, right? The spanning set. So could be 3, right? Can it be more than 3? Why not?
Well, it takes 3 vectors to fill all of R3. So if you have more than that, they'll
Good.
kind of be dependent.
Yeah, I could notice, like, okay, so first thought, S is a subset of R3. So my guess is that the dimension of S is smaller than 3. Could be 3, right? So if you look at those vectors, are those linearly independent?
No.
Why not?
Well, there's an extra one there.
An extra one, yeah, for sure. You can look at that second one and see that it's the first, or sorry, that you can look at the third one and see that it's the first one plus the second one, right? So I could say, all right, so S is also the span of this smaller subset, this smaller set of vectors, 1, 0, 0, and 0, 1, 0. You guys with me on that? Okay, so now I've got 2 vectors. Are these a spanning set? Yeah, they have to be, because all I did was drop a linearly dependent one. Are these 2 vectors linearly independent of one another?
Yeah.
Yep. Okay. What does that mean? That means those 2 vectors make a basis for S. What dimension is S then?
2.
Perfect. So I know that the dimension of S is actually 2. Okay? Now, quick question. What is S?
R2.
Kinda. It feels like R2, right? And this is one of the kind of funky things about linear algebra. Why does it feel like R2?
There's no Z component.
Perfect. Yeah, there's no Z component in here, right? So this is a two-dimensional subspace of R3. How do I know it's a subspace, for one thing? I keep saying that, but I'm not sure that was clear. Why do we know it's a subspace?
The vectors are in 3 dimensions, and also you wrote it at the beginning.
Cool, yeah. If we go way back up to the top, I probably just took this for granted, but a span is always a subspace because it's the set of all linear combinations, right?
Gotcha.
So it's by definition a subspace. All right, so I've got my spanning set. It sits in this like, well, X and Y can vary, but Z has to be 0. What would you describe that space as? Like, if you had to say this in Calc 3, you would say S is the
XY plane.
perfect. It is the XY plane. Is S the only two-dimensional subspace of R3? Is this the only two-dimensional subspace of R3?
No.
Why not?
Well, you could also have the XZ plane or the YZ plane.
Perfect. Those are excellent examples. They are 0.00 repeating percent of all the examples. Why are they 0% of all the examples?
Well, you could also have a plane at Z equals, 1 or 2 or 3 or
Close. So those are good examples. They're two-dimensional things. Are they subspaces?
no, because
Good.
then you wouldn't be able to span it. I see.
Good. So what do they need to have? What's the first thing we check about subspaces that's not even on the friggin' list, but we check it anyway?
0 vector.
Good. So any subspace or any plane containing 0 in R3 is a subspace. The other things might be two-dimensional. That's going to make sense. We could think of a way to make that make sense, right? It seems pretty obvious that if you take a two-dimensional thing and just shift it 1 unit up, it should still be two-dimensional, right?
Yeah.
But it's no longer a subspace. So we're going to have to be just a little bit careful with that, because right now our concept of dimensionality only applies to subspaces because we have to count the basis vectors. Frankly, we probably won't cover it in this class, but there is a good way to make sense of dimension, and it's exactly what you would think for things that aren't subspaces. It's like, if you stood on them locally, how many directions are there to move in? All right, so in answer to, is this the only two-dimensional subspace, I think we've settled on no. Any plane through 0 is a 2D subspace. And then we just have to be careful that planes not through 0 are not subspaces, but that does not make them not two-dimensional.
Makes sense.
Okay. Anything about dimensionality or bases that are confusing here? There should be one outstanding question in your head. Anybody detail-oriented enough to have spotted it? Don't feel bad if you didn't. It's pretty subtle. I have assumed one thing here. I'll give you a clue. I'll go put it on the screen. This is real subtle. Go ahead, Grayson.
I was gonna say you assumed it's non-singular. Or
Oh, yeah, no. What I'm
Or-
getting at is this definition of dimension below that.
okay, gotcha.
Anybody see a subtlety in that? That is a good point, though. I did assume non-singular. The reason I got to assume non-singular is that I said they must be independent, right?
Yeah.
So where's the subtlety in the definition of dimension? Guys see that? There's an A in here. But I just demonstrated a couple of lines above this, right? These are both bases. Okay, see that there's two different bases for R2. How do I know they always have the same number of friggin' vectors in them? That's actually not in evidence here. I'd have to prove that. So I am going to prove that, but I'm not going to prove it right now because I know you guys are probably a little overloaded. But like if I had two bases, the number of things in basis 1 is actually always equal to the number of things in basis 2. And this is just a little bit subtle to show. I'm going to leave this for next time. I want you to see if you can think about this in the meantime. You'll probably notice that this is always true when you're playing around with the homework. It is just a little bit subtle to demonstrate, though. You guys with me on that? All right, cool. I'm going to leave that as a mystery for now. Any other questions about this whole basis thought, dimension thought?